Beginnings. Welcome. Welcome, one and all. I am Nye. I study maths at university, and I find maths really fun and interesting, and I make money teaching maths. I've taught maths for about 4 years now at mostly a high school level. And this is Dom, who I met through running, actually.
Yeah, we met at a run club at the university. For some context, yeah, my name is Dom. I'm interested in maths, but I'm actually a little bit more interested in physics. I study theoretical particle physics, and I also make money teaching maths and physics. I've been doing this for about 5 years, and I've been wanting to make videos to pass on what I've learned over that time. And I met Nye while running, and over several weeks of literally running back and forth around Sydney, we came up with this idea to make a video telling you about triangles, which, okay, might come across as a very simple idea, but we think it's a really neat way of looking at it, and it's a really good way to approach specific problems in mathematics as well.
Yeah, and the idea is really that a lot of very, very interesting maths comes from thinking about seemingly very simple things in a very deep manner. And so throughout the progression of this video is going to be, we're going to think hard about triangles, and hopefully in a way that's accessible to someone of any maths level. And we're going to see how anyone could have invented trigonometry, and how trigonometry, which is really just about triangles, right-angled triangles, because of the way that you can divide up polygons or any straight line shape into triangles, really starting with this very simple idea of triangles can build into almost any shape you want to talk about.
Exactly. So we're really trying to hammer down today, and we hope that if you follow us along the whole way and make it to the end, you'll see that by thinking deeply about the simplest shape that we can draw and really understanding that shape really well, you can understand something about every shape that you can draw down with straight edges.
Well, yeah. Curved edges.
Let's not get ahead of ourselves.
That's another thing. Welcome to measure theory.
That's it.
Yeah, and so you will have to bear with us at the start for a little bit, especially if you're quite familiar with high school maths, but we promise we'll get to some very interesting ideas and hopefully build an intuition of things you might not have thought about in this way. And so
Yeah.
the leading question, the motivating question of the video is, what is the minimum amount of information you can know about a triangle before you know everything about it? And everything being maybe 3 types of properties. We're going to think about side lengths, we're going to think about angles, and the area of the triangle.
Exactly. So maybe at first thought then, you might think that, okay, there are 3 angles in a triangle, there are 3 side lengths in a triangle, and then there's this property of area in a triangle. So you might think that there are 7 things, right, which we can know about a triangle. But the aim of the video is to tell you that if you know 3 things about a triangle, you can know everything about the triangle. And we're really going to establish this idea. So that means that there are 4 properties of a triangle which end up being dependent on the other 3.
Yeah, we don't need them. Throw them out.
Exactly.
So, well, let's just start off. And John, what if we just had a right-angled triangle?
A right-angled triangle. Well, yeah, if we start off with a right-angled triangle, then we know that one of the angles is 90 degrees. And maybe I should interject here and say that there is one defining property of a right-angled triangle that we can know. And that is that the sum of all of the interior angles is equal to 180 degrees. You can check this by drawing any triangle that you like on a piece of paper and just measuring the three
Right.
angles. You'll always find that their sum is 180 degrees.
This isn't
And
just true of right angles. This is any triangle.
this is any triangle, exactly. So when we have a right angle triangle, right, we know that one of the angles is 90 degrees. So that means that if we know another angle, then necessarily we'll find the third angle, okay, because it's related to the other angle, such that the sum of all three angles is 90 degrees. So the sum of the other two, did I say 90 degrees? The sum of all three angles is 180 degrees. So the sum of the two unknown angles is 90 degrees. Anyway, I think we're getting ahead of ourselves talking about these angles. And what we're really interested in is trying to figure out what the minimum amount of things we can know about this triangle is so that we know everything. So I can ask the question, okay, we know that it's a right angle triangle, so it has this 90-degree angle. And perhaps we know the length of the hypotenuse, which is the longest side and just so turns out to always be opposite the right angle. We can ask ourselves the question, is this enough to know everything about the triangle? And the answer to this question is easily demonstrated by considering a ladder standing up against a wall. This ladder will form a right-angled triangle against this wall, and we'll know the length of the ladder, so that is, we'll know the length of the longest side. But we can notice that if we put the ladder at different angles to the wall, it'll form triangles of different shapes. So, in other words, there's lots of different triangles that we can form by knowing the hypotenuse, the longest side, and that it's a right-angled triangle. This naturally leads to the question, well, what other thing can I know about this triangle to know that it's a fixed shape? And maybe you can imagine that if you have a ladder of a fixed length and you have a wall of a fixed height that you need to get up, then there's only one way in which you can link the wall to the ladder, and this will form a triangle which only has this specific shape. So what this means is that knowing that it's a right angle triangle, knowing one of the side lengths and knowing the longest side is enough to know exactly the shape of the triangle. And since we know exactly the shape of the triangle, we could draw it, okay? If we're considering a ladder, then maybe we won't have enough paper to draw it. But we could get our tape measure out and we could measure the other side length of this triangle. And we could get a protractor out and we could measure both of the angles in this triangle. So that is, we've just found that knowing that it's a right angle triangle, knowing the hypotenuse, the longest length, side length, and knowing one of the other side lengths is enough to know everything about this triangle. Why? Because we could just measure it.
Yeah, I mean, and that's one of the sets of minimum things you can know about a triangle. And there are three more. There are four in total. And so, moving on, let's throw away the ladder. Throw away the right angle triangle. What if we just knew two side lengths of any triangle? Right? Is that enough to know everything? And this is a bit of a leading question. Perhaps you're already guessing the answer, but you can imagine the third side swinging around with those two sides. And with that intuition in mind, the answer is no. You need the angle between the two side lengths you're given, and this fixes the rest of the triangle in place.
So now we know two ways where we can only know three things to know everything about the triangle.
Right.
And I'm going to tell you about a third. So considering Nye's example, where we knew two sides, the included angle, and another side, we can imagine that, okay, bear with my arms, there's the angle included between my fingers and my elbow, and this side, which can move along. And we notice that as we change the angle, we change the shape of the triangle. We can imagine that this is exactly the same as changing an additional imaginary side length, which exists between this elbow and this hand, okay? As we increase the size of the angle, the side length which connects there increases. So that is, instead of knowing the angle between my fingertips and my elbow, we can instead know the other side length between my elbow and my other fingertips. Okay, so that is, we can know exactly the shape and hence everything about a triangle by simply knowing three sides.
Right. Okay. And now, as our final idea here, what if we know two of the angles of any triangle? Well, then automatically we know the third because we know their sum is 180. But is that, have we just found a way of only knowing two things about a triangle and knowing everything? And if you draw these on paper, as I encourage you to, then it might seem at first like yes, but you can imagine having a triangle of the same shape but of different size, right? And these are not the same triangles, and so you require two angles and then a side. And once you have those two angles and a side, then this is the minimum amount, and you know everything about this triangle. And so,
Exactly.
if you're very familiar with high school maths and geometry, then you will know these congruency tests. For two things to be congruent, they are exactly the same. And a good way of thinking about it is, if you imagine these shapes as pieces of paper, then you could put them on top of each other, and they would be identical, right? They would be the same shape.
Exactly.
And in this way, you get an idea of how we don't really care about rotations and flipping. And if you're playing around with these, you might find two triangles that look, at first glance, like different things, but really a bit of rotation, a bit of flipping, and they're the same thing.
Yeah. So what we've established so far is this idea that once we know three things about a triangle, we've exactly fixed its shape. And we've just been claiming that that means that you know everything about a triangle. And the way that we can think about this is that you could just pick, for example, three side lengths and draw a triangle and verify that this is the only such triangle with these three side lengths, for example, right? You could have picked any of the congruency tests, verified that this is the only such triangle that you could draw, and then measure the angles and notice that these angles are exactly fixed by these side lengths. And okay, it's a little bit hard to just measure the area, but you can imagine that the area is also fixed because this triangle has a fixed shape.
Right. But thinking about the shape of it, and going back to this example where you know the angles, we know that if you know the angles, then you know something about the way this triangle is going to look. You know something about its shape, but perhaps you don't know something about its size yet. And so there can be two triangles where you just know the angles, but they have a different size. One has been scaled up. And so, arbitrarily, we're going to talk about right angle triangles now, and we're going to talk about knowing their angles, but really we're talking about knowing angles of any triangle. And we'll get to...
Exactly. And the reason that we're considering right angle triangles here is just because they're easy. Okay? Right angle triangles are easy. So if we don't know the problem for more complicated triangles, let's try and simplify the problem and understand the problem very well from a very simple case. And maybe, as you'll find out later, this case will have applications to find a more general thing.
Yeah, and this is a common theme in maths. So imagine you have this right angle triangle, and you fix the angles. The angles are the same, but you imagine this right angle triangle getting bigger and then smaller again, and you notice that the shape is always the same. And in fact, if you were to divide one side length by another side length, then these would always be the same fraction. In other words, these triangles all have the same ratio of side lengths. And so, clearly, there is some link between the angle, or the angles of this triangle, and the ratios of these side lengths, because the ratio is always the same, no matter what the triangle size is. And this idea is really the key idea of the video, and so we might go over it again. Hit me, Dom. What you got?
Yeah. So the idea is that we found this transformation between triangles with the same angles, but of different sizes. So what that means is, and this actually is one of the key properties of geometry or triangle geometry, in that we know that similar triangles, so that is triangles which have the same angles, have their side lengths scaled by the same factor. Okay, that's why small triangles with the same angles look the same, okay, up to some size difference, as big triangles with the same angles. So the idea is that all of the side lengths of a big triangle compared to a small triangle, which are similar, are scaled by the same factor. And what this allows us to do is to notice that two similar triangles always have their sides, if you match up the sides of different similar triangles, the ratio of corresponding sides is always the same. So coming back to this right angled triangle example that Nai was mentioning, if we consider a right angled triangle where we're trying to find a relationship between this angle and the side lengths, for example, then what we can do is we can consider a bigger triangle which has the same shape, so that is, it's a similar triangle, and we can notice that these two similar triangles both have the same ratio of sides. So for example, we could consider the side opposite the angle and the hypotenuse. So the ratio of, say, the opposite over the hypotenuse must be exactly the same for each of these triangles. Now, we can see that in this scenario, this angle is exactly the same for this specific setup, and this ratio of sides is exactly the same. So what does this tell us? It tells us that we must be able to find a relationship between the angle and the ratio of sides. And believe it or not, this is exactly what trigonometry is. It's just asking the simple question, or rather, it's the answer to the question that I just asked. What is the relationship between the angle and the ratio of sides? Because we know such a relationship must exist. What would you call such a relationship, Nai?
Well, I'm not one for names, but why don't we call it something like, I don't know, sine, but very confusingly spell it like sin, the English word for, you know, all the good things in life.
That sounds like a terrible idea.
Yeah, well, this is the idea of trigonometry. This is it. If you're following with us now, you've invented trigonometry, more or less.
Exactly. And unfortunately, we don't have the naming rights for these specific functions. They've already been named, so we do need to call them sine, cosine, and tan, where each of these just correspond to different ratios of sides in a right angled triangle, right? We were able to show via intuition that there should be a relationship between the angle and the ratio of side lengths. And then just answering the question, well, what is that relationship, leads us to sine, cosine, and tan. Now, I want to bring to your attention how trigonometry was done before calculators, because now you just, whenever you have a problem like this, and I'm sure most of our audience has seen this before, but even if you haven't, you'll notice that there are these buttons on your calculator that say sine, cos, tan, and they basically answer the question, okay, if I know the angle, can you tell me the ratio? And then you'll put tan of that angle, and then it'll tell you what the ratio of the opposite of the adjacent side is. But imagine before calculators, what are you going to do when you want to answer that question? Well, the answer to that problem is just get lots and lots of people drawing triangles, right angle triangles of different shapes, and measuring the angle and writing down the ratio. Okay, so that is, they draw a right angle triangle, they measure the angle, and then they measure the two side lengths that are of interest. For example, the opposite and the hypotenuse. They divide the opposite by the hypotenuse, and they say, okay, for angle, say 30 degrees, the opposite over the hypotenuse is 1/2. Okay, I've found that out. I know it forever. Let's throw it in a bag and, or not even a bag, you'd write it in a textbook. And in fact, this was done for centuries.
Yeah, there were these huge tables of these things. I mean, imagine doing maths before calculators. Imagine that being your job. This would be some some fun work, right?
Yeah, all all your job might have been, say, several hundred years ago, was drawing a very precise triangle and then measuring the angle and the side length to as many decimal places as you could.
Yeah, well, everyone needs a hobby. Yeah, and this is trigonometry, and it seems really scary, but hopefully this is the intuition behind it.
Exactly. And the idea is that we were able to work out these things for right-angled triangles, right? The ancients could have done it 2,000 years ago by just drawing down all these triangles. Right now, your calculator has it all stored in memory. But we know something now. We know a quantitative way to get from an angle to a ratio of side lengths. And this is very powerful because while we've only proven it in right-angled triangles, you might notice that knowing it about right-angled triangles is extremely helpful for non-right-angled triangles. Why? Well, because non-right-angled triangles can always be drawn as two right-angled triangles.
Right, exactly. And, you don't believe us. Fine. I mean, take a little offense, but that's all right. You should always be skeptical in maths. Draw it on a piece of paper. And so we've worked from right-angled triangles to normal triangles. And then as it turns out, from normal triangles, you can work with any straight-lined shape. Any polygon can be divided into triangles. And so we've started with something very small, and now we're talking about things that can be very big and very complicated. And the same rules are going to apply, the same trigonometry that we just invented. It's going to tell us all kinds of things.
Exactly. Now, you can actually apply these ideas, and there was a reason that we wanted to develop right-angled trigonometry. Okay, firstly, it's very helpful in non-right-angled trigonometry. That is, I keep saying the word trigonometry, but really it's just the study of triangles, let's say. Once we know something about these right-angled triangles, we know something about non-right-angled triangles. But notice that 3 of the 4 congruency tests that we'd established earlier were completely general. We didn't care whether it was a right-angled triangle or not a right-angled triangle. So for example, we developed this side-angle side test, which said that if you know a side, the included angle on the other side, then you must know everything there is to know about this triangle. So what that means is that we should, in principle, be able to find out the other 2 angles, the other side length, and the area of this triangle based on just these 3 pieces of information. And in fact, you can prove relationships between these things using the right-angle trigonometry that we've just established.
Right. If you were to prove a result, and you were to just pick one out of the air, which would you pick?
Well, let's just say we want to find out the area of a triangle where we know 2 side lengths and the included angle.
Okay. Well, then this is where, if you've, I don't know, around here would be about year 10. If you've done that year 10 trigonometry and geometry, then this will be the sine formula for area.
Right. Can we prove it?
Yeah, sure. How would you do that?
All right. Well, we'll cut to that in a second.
Cut.
Okay, so now I'm going to put my money where my mouth is and show you how you can write down a formula for the area of a triangle given two sides and the included angle. So far, I've got on the screen everything that we can know about a right angle triangle. That is, how we can find a relationship between the angle and a ratio of two of the sides. And these are neatly expressed in terms of our trigonometric functions, sine, cosine, and tan. Now, the aim is to find the area of a triangle knowing two sides. So, two sides and the included angle. So what I'm going to do is I'm going to draw such a triangle. So here we are. We have a triangle with two sides, okay? And it has an included angle, which I'm going to label by theta. Okay, I'm going to call the two sides x and y, okay? And I hope that you notice that based on our previous discussion, that this side length here is completely fixed. And in fact, right, we could apply this same method, which I'm going to show you, to actually figure out what that side length is. Trying to use this method would arrive at the cosine rule. And I would encourage you to do so. Now, what we can notice is that if we decompose this non-right angle triangle into two right angle triangles, as I've just shown you, where I can call this this side H, then we realize that we can use what we know about right angle triangles to actually express the area. In fact, okay, something which I'll assume that you know, it's that the area of any triangle is equal to half times the base times the height. And in the way that I've just drawn H, this is going to be 1/2 HY. Now, the problem that we have right now is that H is not one of the variables that we wanted to express our area in terms of. We want it in terms of X, Y, and theta. This side angle side that you'll notice here. So what we're looking for is an expression for H in terms of, say, X and theta. And we can exactly use this formula here to write down this expression. So considering this right angle triangle, we know that sine theta is equal to the opposite side, which in this instance is H, over the hypotenuse, which in this instance is X. Doing some rearranging, we notice that H hang on, I've just noticed that my video is in front. Let me write this out again. We can write down that sine theta is equal to H over X. And doing some rearranging, we can see that H is equal to X sine theta. Okay. Using this expression for H and plugging it in here, we arrive at our area formula, xy sine theta. Okay? And that's it. We were just able to write down the area of this triangle in terms of the side that we knew, the included angle that we knew, and the other side that we knew. Okay? So we're not all talk. You can actually write down explicit relationships for the things that you don't know if you know the correct three things, which are derived from these congruency tests. Okay. This principle is completely generic. You can apply it to prove the sine rule, the cosine rule, etc. And I would encourage you to give it a crack, where every single time you're using this proof, all you're doing is decomposing your triangle into two right angle triangles.
All right. You happy to?
Yeah. Do we want to do some kind of conclusion?
Come back for more. Peace. What do you want to say?
We love you, America. What's got three sides, three angles, an area?
Is it my mother?
No, your mother's lovely, and she's got several dimensions. She lives in more than two.
Well, thank you. I'm glad you speak so highly of her. All right,
Yeah, are we wrapping it up then?
we're wrapping it up. We're wrapping it up.